Well, good day. My name is Philip Wood. I'm a general surgeon with an interest in histology. I've spent most of my professional life in the middle of Africa, Democratic Republic of Congo, where I've had a particular interest in histopathology and set up a histopathology lab, and I still read slides that they send me by email. Today, we're going to look at the blood circulation. You'll see several slides of text and followed by some illustrations. The text is a very brief synopsis of what you need to know to be a good doctor, what you need to know to succeed in the exams, and I would encourage you to copy into your notebooks as much of the text as you possibly can. There may be some illustrations that you want to sketch, but copying the written text is the most important. Now, let me share my screen and run through this presentation. The circulation system. We're talking about blood vessels. The cardiovascular system includes the heart, and we'll talk about that next talk. The arterial system, venous system, capillary system. The arterial system carries blood from the heart down to the capillaries in either the body or through the lungs. And this system includes some large arteries. These are elastic arteries, some middle-sized arteries, muscular arteries, and small arteries and arterioles. Then there's the venous system, carries blood from the capillaries back to the heart, and several different names here: venules, small veins, medium veins, and large vena cava, Latin name for large veins. Capillary system is between the arterioles and the venules, very fine blood vessels which form capillary beds, where the exchange of gases, where oxygen is given to the tissues and where CO2 is moved into the bloodstream, and where some blood cells, white blood cells, can actually move out from the blood vessels into the tissues. The blood circulates in two different routes. There's a systemic circulation, that's to say oxygenated blood from the heart goes out to all the organs and tissues of the body. And then there is the pulmonary circulation, which sends deoxygenated blood to the heart, from the heart to the lungs for gas exchange, and then returns the oxygenated blood to the heart. So this is a little illustration of those two circulations, the pulmonary circulation and the systemic circulation. The pulmonary artery there, which takes blood from the right ventricle, here's my mouse to show you, right ventricle up into the lungs. CO2 is given off, oxygen comes in, blood changes its color to bright red, left atrium down to the left ventricle, out into the aorta, down through the rest of the body, gives up its oxygen there, takes in carbon dioxide, and carries the blood back to the heart, in through the vena cava, and back to the right ventricle, back to the pulmonary artery. Now, each side of the heart pumps about 100 milliliters of blood at each pumping. If your heart is pumping at 60 times a minute, that'll mean 6 liters will go through the circulation in a minute. That's the whole of your blood volume will do a circuit of the body in 1 minute. How do we measure the circulation? Well, we measure it in beats per minute. You can measure your pulse in your radial artery. Normal is between 60 and 80 beats per minute. And we measure it by blood pressure. Blood pressure is normally given as two figures, an upper figure and a lower figure. The upper figure is the pressure in the large arteries at the time of heart beating. That's what we call systole, when the heart makes a beat, and the high number for blood pressure is the systolic blood pressure. And if there is a maximum normal, 140 millimeters of mercury, or if you like, 14 centimeters of mercury, same thing, we measure pressure according to the height of a column of mercury. If there's a maximum, then there must be a minimum. The maximum is maintained by constriction of peripheral muscle arteries, but the minimum shouldn't go below 60 millimeters of mercury, and that's a minimum when the heart is relaxed, when the heart is in diastole, and we call that the diastolic blood pressure. Systolic blood pressure and diastolic blood pressure. And it's the elastic arteries which maintain that diastolic blood pressure. You could imagine that when the heart's not beating, the pressure in the blood vessels goes right down to nothing. But no, it doesn't go down to nothing. The elastic arteries swell when the blood is pushed into them, and they slowly decrease in size and maintain that diastolic blood pressure until the heart beats again. Now, this is what an artery looks like. It's in three layers: an intima, a media, and an adventitia. The intima is shown there in blue, a layer of endothelial cells with an elastic or a basement membrane, and then a media, a thick layer of elastic and muscle fibers, and then a layer of adventitia of conjunctival tissue on the outside. Blood vessels have three layers, three tunics, three layers, three tunicae, if you want to use it, the name in Latin. The innermost layer is called the intima. The intima, this layer contains the endothelial cells and some subendothelial connective tissue may contain an elastic lamina, internal elastic lamina, in some vessels, but not in all. So the most important thing in the intima is this layer of endothelial cells, a simple epithelium, just one cell thick, and these are cells with a lot of cytoplasm, one small nucleus, and they join up and have tight joins between one cell and another, which are waterproof and don't let the blood pass through them. The next layer on top of the endothelium is the media. Middle layer is called the tunica media, contains smooth muscle cells arranged in a circular fashion. There usually are some smooth muscles, but there may be a lot of elastic fibers as well. And it's the contraction and relaxation of smooth muscle cells which will change the diameter of the peripheral vessels and will affect blood pressure. And then the outermost layer is the adventitious tunica, a layer of connective tissue dominated by collagen and some elastic fibers. And it's found in large and some medium veins The adventitious tunica may also contain bundles of longitudinal smooth muscles. Here's a section of a blood vessel. What can you see? Well, I hope you can see the three layers. On the inside here, on the inside is the intima. And the intima is just, in many vessels, it's just one cell thick. And this is the cytoplasm of the cell. Difficult to see any nucleus. Maybe that's a nucleus here. The cell hasn't stained too well, and this particular stain that's been used here, it's a stain which has been used to show this middle layer here. This is the media, and it's a particular stain which shows elastic fibers. You can see the elastic fibers in this artery. So this is obviously an artery which is lying close to the heart, contains a lot of elastic fibers. There will be some smooth muscle cells here as well, although they don't show up well in this particular stain. And then on the outside is the adventitia, and maybe this is a small little blood vessel here which is supplying the wall of the artery. Normally, arteries, veins, capillaries get their oxygenation, get their nutrients from the blood which is inside the artery, but for large arteries, they need extra blood vessels on the outside in the adventitia here. These, I presume, are some nucleus of some of the cells over there. A large artery in section. So we have elastic arteries, and that means that they contain a lot of elastic fibers in the media, and that elastic artery comes from the carotid arteries fairly close to the heart. The media that you've just been looking at has several layers of elastic lamellae, which are well organized in a concentric fashion around the blood vessel. They're seen there as parallel wavy black lines, and those are the elastic fibers. Smooth muscle cells are present, but they're not visible with this type of staining. The adventitious tunica on the outside consists of connective tissue, collagen, with a small number of elastic fibers and some fibroblasts. Elastic arteries are arteries which are close to the heart, and they're important in maintaining diastolic blood pressure. Here's a muscular artery, and this is in a much more usual H and E stain, hematine and eosin. Hematine stains the nuclei blue or purple, and eosin stains the cytoplasm pink. Here's at the top of this slide here is the lumen of this artery, and you can see it's full of these red circles. What are these red circles? Well, of course, those are red blood cells. They don't have a nucleus. They're just a little sac, a biconcave disc of hemoglobin. There are one or two white cells here, one here, and one here, one here. These look like polymorphs to me, and this may be a lymphocyte in there. So inside here we have the endothelium, and the endothelium is represented by these nuclei. And maybe this, in some places you can see a little bit of cytoplasm, but those are the nuclear, those are the cytoplasm nucleus of the endothelial cells. And this is the internal elastic lamina in this particular artery. This is prominent. This is elastic fibers which hold the artery together and allow for some expansion if a larger volume of blood is needed. But these in the intima,
in the media,
mainly smooth muscle cells, central nucleus in a elongated fusiform quantity of cytoplasm. And then on the outside, here's the adventitia. This is collagen fibers again, some fibroblasts. Here's maybe another small blood vessel, a vasa vasorum there, which is supplying blood to this artery. A muscular artery, quite different from the elastic artery that I showed you before. This is a muscular artery, important in controlling systolic blood pressure. Muscular arteries are basically the same structure as elastic arteries, but they contain a lot of smooth muscle cells in the middle layer of the tunica, in the media, many more smooth muscle cells than in elastic arteries. Muscular arteries are the periphery of the arterial system, and they're important in controlling systolic blood pressure. You needn't worry too much about this, but this is an electron microscope view of the same type of artery that you've just seen. You can see again the red blood cells which are in the center of this artery, and very obvious that they're biconcave discs of hemoglobin. This is a central depression in the red blood cell. Here are the endothelial cells on the inside. Here is the internal elastic lamina, and here is the media with the muscle cells, particularly smooth muscle cells, which are filling up this media. So the main message is that arteries, veins, capillaries all have a similar structure. They all have intima, they have a media, they have an adventitious layer on the outside. The three layers are there in each of those three types of blood vessel: artery, vein, and capillary, but the quantities of tissue varies considerably. So the media is very thick in an artery, it becomes much thinner in a vein, and it may be almost invisible, maybe just represented by an occasional cell in a capillary. The endothelial, the intima, is always present in every single capillary, and the endothelium may, in some very, very small capillaries, just be one single cell, which is formed round into a circle and makes up a very, very small capillary. I will show you one like that in just a moment. Here's a vein, a much thinner wall. 60% of your blood volume is contained in the veins. They can dilate. They're much wider channels than the arteries. And they have valves. They only allow blood to pass in one single direction. If blood wants to try and come back the way it came from, then these valves will close, and it's not possible for the blood to descend in these veins. No veins in, no valves in an artery here. Endothelium on the inside, some basement membrane, internal elastic lamina, sometimes complete, sometimes very just minimal amount of elastic tissue in some of the muscular arteries. But we've just seen two examples where the internal elastic lamina was quite important. Tunica, media, the media can be smooth muscle, can be elastic. There is another external elastic lamina sometimes, and then there is the adventitia on the outside. So I mentioned already vasa vasorum. These are small blood vessels found in the adventitia of very large vessels in order to provide nutrition for these large vessels. Normally, vessels get their oxygen, remove their carbon dioxide, get their glucose, whatever else they need, from the blood which is inside the blood vessel. But very large, thick blood vessels like the aorta have to have these vasa vasorum, and they supply oxygen and nutrients to the large vessel walls. And here's another example. Again, endothelium on the inside, just one single layer of cells, represented here by several nuclei, difficult to see the cytoplasm there. Here's the media. This looks like a combination of some elastic and some muscle fibers here, beautifully arranged elastic fibers in parallel, and then these dark blue areas, these are nuclei of smooth muscle cells. Here are the vasa vasorum, and here's the adventitia on the outside, and these are small little blood vessels which are supplying oxygen to this large artery. And then we come to capillaries. The arteries end in capillaries. These are multiple branches of the artery, and the vessels get smaller and smaller and smaller. And this is where the exchange of gases and nutrients and other materials occurs in the capillaries, these small blood vessels. And there are three types of capillaries that you ought to know about. Continuous capillaries, which have complete endothelial cells and a continuous basal membrane. And these are, we would say, waterproof. They don't allow any blood products to escape from them. They're continuous capillaries. But there can be some pores or holes in the capillaries. They have endothelial cells, but they are perforated with small pores which allow some products to pass through, some glucose, some immunoglobulins, and from time to time some white cells even can pass through these capillaries by a process called diapedesis. But these are not tightly closed capillaries the way the continuous capillaries have got waterproof walls. And then there's a third type of capillary called a sinusoidal capillary or a discontinuous capillary. And they have very incomplete endothelial cells and have very large pores, and part of the cytoplasm may be missing. And you see these discontinuous sinusoidal capillaries only in certain organs, and particularly we think of the liver and the spleen. And the sinusoidal capillary is often lined not by endothelial cells, but lined by the hepatocytes, lined by the cells which make up the liver. And these liver cells are in direct contact with the blood in these sinusoidal capillaries. There are endothelial cells there, but they are discontinuous. They don't join up one with the other. So here's an illustration of these three types of capillaries. The continuous capillaries have endothelial cells which are tightly joined one to the other, sitting on the basement membrane. You have the fenestrated capillaries, which have small holes in the endothelial cells sitting on a basement membrane. And then the sinusoidal capillaries, discontinuous capillaries, have much larger holes, and they have an incomplete basement membrane as well. And those holes, if you like, in the capillary are filled with liver cells or red bone cells, lymphoid tissue, and cells and proteins can easily pass out from that into the organs in which you find these sinusoidal capillaries. Here's a very thin section of some conjunctival tissue showing a small capillary. What can you see inside the capillary there? You can see this red thing here. Well, this is a red blood cell. And you can see actually the red blood cell is smaller than the capillary. Red blood cell diameter is usually 7 microns, 7 to 8 microns in diameter. Well, this little capillary must be less than 7 microns in diameter, and the red blood cell has to squeeze. It has to be squeezed tight to get through this capillary, and you can imagine how red blood cells get damaged when they pass through capillaries which are quite so small, and that's a reason why red blood cells only have a lifespan of about 4 months, 120 days. They have to be removed and replaced by the spleen by red blood marrow. So this capillary here looks as though it's just made up of endothelial cells alone. Can we see this is probably a nucleus of an endothelial cell down here, and this is cytoplasm of the endothelial cells on each side. There really isn't very much evidence of any kind of a media, no evidence of any adventitia on the outside. These capillaries are made of endothelial cells. You can see the nuclei of fibroblasts, and there's some fibers here, collagen fibers, in this conjunctival tissue here, in which these red blood cells and these capillaries are passing. So, not to stress this too much, but the endothelium is the most important part of a capillary, and it's most commonly these endothelial cells are joined tightly one to the other, and the lumen is only big enough very often to let one red blood cell go through at a time. Very small opening there. So what are the functions of the endothelium of blood vessels? Well, they provide a permeability barrier, and they stop many products from leaving the blood and from passing into the interstitial tissue fluid. But water, electrolytes can pass, and they're what make up the interstitial tissue fluid. The interstitial fluid is continually being added to by passage of water and electrolytes from the bloodstream through the endothelium of capillaries. The endothelium can allow the movements of leukocytes as well, and immunoglobulins into the tissues. Leukocytes only in certain conditions, when there's inflammation, when the leukocytes, the white blood cells, can get out into the tissues in order to combat infection or other illness. The endothelium is what provides the growth of new blood vessels. If you've had a cut, part of the healing process will be for new capillaries to be formed from endothelial cells. They multiply, they produce new capillaries which enter into the blood clot or wherever there is in the wound, and will allow for healing and restoration of scar tissue. Endothelium provides signals that regulate the tone of adjacent vascular smooth muscle cells. And these signals are largely um, enzymatic signals. Various enzymes are discharged by the endothelial cells, and that changes the tone of adjacent vascular smooth muscle. Endothelium provides anticoagulant signals that inhibit platelet attachment. This is always a big problem in the circulatory system. You want the blood to clot, you want the blood to solidify when it leaves the circulation system, otherwise you'll bleed to death, but you don't want it to clot or to form platelet aggregates whilst it's circulating in the circulatory system. So blood clotting mechanisms are extremely complicated. There are many, many factors that have to come into play before blood will clot, and we will be needing to be talking about that sometime or other. When endothelial cells are injured, they reduce the production of platelets inhibitors, and that means that platelets can then get together, they can be activated, they can stick together and form platelet nails, platelet plugs that plug up holes when the endothelium is injured. And there are other inhibitors of there are other substances which reduce the production of platelet inhibitors, such as thromboplastin, which is another enzyme which is released whenever the tissues are injured. Exposure of underlying basal lamina and connective tissue further stimulates platelets to adhere, to aggregate, to block the passage of blood out into a wound. So there is a microcirculation. There is a flow of interstitial fluid through the body between blood vessels and cells. And not every cell has an immediate attachment to a capillary. So if that cell needs oxygen, the oxygen will be provided through the interstitial fluid. Oxygen leaves the capillary, goes into the interstitial fluid. That fluid bathes the cells in the vicinity, and then that fluid can be reabsorbed into the circulatory system a bit further on. So that's how the cells get their oxygen, how CO2 is removed from them, how they can remain in good, healthy condition. This is a picture of that interstitial circulation. Is the blood flowing down from an arteriole into a capillary? And this is an area of high pressure from systolic pressure from the beating of the heart, and that will tend to push interstitial fluid out through the wall of fenestrated capillary, push it out into the pool of interstitial fluid in which all the cells of your body are bathed. As the blood passes through the capillary, the blood pressure, the pressure in the capillary gradually falls and falls and falls. And down here at the bottom, the blood pressure, the pressure in the capillary, sorry, I didn't mean to do that. The pressure in the capillary is a lot lower, and there is an osmotic pressure that pulls the interstitial fluid back into the capillary, pulls it back into the capillary. So this hydrostatic pressure pushes out water electrolytes, but the plasma proteins are maintained on the inside, And it's the plasma proteins that exert some osmotic pressure and pulls the interstitial fluid back into the capillary system. If I could give you some figures, and maybe these are not correct, but the blood pressure up here might be in the region of 15 millimeters of mercury. It's dropped a lot since it left the heart. It's down to about 15 here at the top. The plasma proteins in the blood exert an osmotic pressure of about 10 millimeters of mercury. So 15 minus 10, pressure of 10 pulling it in, a pressure of 15 pushing it out. There are 5 millimeters of mercury tending to push water out into the interstitial fluid. Now, if the pressure down here is 5 millimeters of mercury at the far end of the capillary, then there is 10 millimeters. We said there is 10 millimeters of osmotic pressure here, tending to pull liquid back into the capillary again. So there will be 10 minus 5, there will be 5 millimeters of hydrostatic pressure tending to pull the interstitial fluid back into the capillary again. So this is the capillary microcirculation. This is an illustration of discontinuous capillaries, sinusoidal capillaries in the spleen. And you can see these relatively large spaces here. Here are the splenic cells. You can see their purple nuclei very easily. But on the inside here are lots of red blood cells. And these are discontinuous capillaries in the spleen. And the red cells here are in direct contact with the splenic cells. There will be some endothelial cells around here. There will be some basement membrane as well, but in discontinuous capillaries, the blood can come in direct contact with other cells. So this is somebody's illustration of what a discontinuous capillary might look like. Here are the endothelial cells on the inside of the capillary, but there are lots of gaps between them, and the basement membrane, basement lamina is quite incomplete as well, doesn't form any barrier to the red blood cells and other things passing through this capillary and into the liver or the spleen. We're noting the differences between arteries and veins. The artery has a rounded lumen, whereas the vein has a larger oval or irregular shaped lumen. It has a much thinner wall than the artery has. The artery has a thick wall, vein has a thin wall. The artery, the tunica media, the media is much thicker than the adventitia, but in the vein, the adventitia is often much thicker than the media. In some small veins, the media may be almost invisible, and particularly in capillaries, of course, the media is almost invisible. Circularly oriented smooth muscle cells form uniform sheets in the tunica media of the arteries. However, smooth muscle cells are much fewer and don't form a distinct sheet in the vein. Valves are present in many veins, especially in the median veins of the extremities. Their function is to prevent gravitational backflow of blood into the distal parts of the veins. It helps blood get back to the heart. Arteries don't have any valves except the beginning of the aorta, the beginning of the pulmonary artery where they leave the heart. We can classify veins. Superficial veins are close to the surface of the body, have no corresponding arteries, and deep veins are deeper in the body, often have an artery running beside them, and they're at a much higher pressure. low pressure superficial veins, high pressure deep veins. And there will be communicating veins between the two, between the superficial veins and the deep veins. But these communicating veins will have valves. They have valves to stop blood flowing from the high pressure veins deep inside to the superficial veins on the surface. And blood can flow from the superficial veins into the deep veins, but not vice versa. There are pulmonary veins, and the pulmonary veins deliver oxygenated blood from the lungs to the heart. Veins normally carry deoxygenated blood. We show them as blue lines on a chart because the blood is usually blue, but pulmonary veins contain oxygenated blood. They contain bright red blood. And there are systemic veins, and as I say, systemic veins usually deliver deoxygenated blood. They contain blue blood. I think this is the slide that I wanted to show you earlier. You've got a vein here on the right and a artery on the left. The artery with a thick media, the vein much thinner media here. The vein, you can see the red blood cells on the inside, a few red blood cells on the artery here. This artery has got a thick external elastic lamina as well as a thinner internal elastic lamina. This artery doesn't have much in the way of adventitia. I don't know, a little bit more adventitia around this vein. It's in adipose tissue. These are fat cells here. That's one single cell. It's just a little bit of cytoplasm, pink on the outside, with a nucleus in here somewhere. But this is just a big fat globule inside a cell. And this makes up adipose tissue with a certain amount of fibrous tissue, conjunctival tissue mixed in with it. There's a nerve down here. I'll show you a nerve in one of the future lectures, but around myelin sheath with an axon with a nerve prolongation in the middle of it there. So veins have valves, and particularly those veins in the arms and legs, they have one-way valves that allow blood to pass towards the heart, but not back out into the system. Each valve has got two flaps or two cusps or two leaflets, whatever you want to use, and the edges of these valves meet and block off the vein completely so that blood cannot descend into the lower parts of the body. Blood, as it moves towards the heart, pushes the cusp open like a pair of one-way swinging doors, and you can walk through that door very easily, but when the door closes, difficult to close, walk back through the door in the opposite direction. If gravity or muscle contractions try to pull the blood backwards, the cusps are pushed closed, preventing backward flow. So by opening the valves, the blood flows towards the heart. By closing, it can't flow back. And exercise is the most important thing in venous return. Venous blood does not get back to the heart because of the pumping of the heart. No, the heart can pump blood out to the capillaries, but by the time the blood gets there, blood pressure has dropped virtually to zero. And it's exercise that brings blood back to the heart. We're going to talk just a little bit about varicose veins, and the problem with varicose veins is that these valves in the veins do not work the way they should. And normally blood cannot flow, as you see in the normal vein, it can't flow back, but in a varicose vein, it can flow back. Normally, the valves close and blood can flow in only one direction in a vein. But if there are varicose veins, then blood can flow back the way it shouldn't, and that leads to enlarged, tortuous veins, particularly in the legs, varicose veins. And the cause of varicose veins is the fact that these one-way valves are not working the way that they should. So you have two systems of veins. We talked about this already. We have low pressure superficial veins located just under the skin, and high pressure deep veins located in the muscles and along the bones, and connecting veins which link the two. And a breakdown of these veins, which are also known as perforators between the superficial and deep veins, is often the cause of varicose veins. Here are the perforators. The deep veins down below here, superficial veins above, and a perforator which will allow blood to pass from the superficial system into the deep system. But if the perforator valve is open, then you can get a varicose vein here. It enlarges, becomes wider and longer, and you get these tortuous veins on the surface of the body. So how does blood return to the heart? Well, it returns because of exercise and the skeletal muscles, rhythmic contraction of limb muscles, squeeze the veins, and blood is forced to move in these veins. It can't go back because there are valves which stop it going back, so it has to go up. It has to go up to the next level, and it's the muscle pump which pushes blood from below up above. As muscles move, they squeeze the veins. Because of the one-way valve, the blood can only go in one direction, up, and it's pushed up a seeming ladder. There is also a thoracic pump action. When you breathe, you get a negative pressure inside the chest, and that does tend to pull blood towards the heart as well, but it's less important than the skeletal muscle pump in the periphery. So extremely important that you exercise, particularly exercise after operations, and get your muscles moving. Here a nurse helping somebody to walk after an operation. One last set of veins that we haven't talked about, portal veins. Portal veins start like any other vein from branches, come from capillaries, many capillaries that join together to form venules, very small veins. The small veins join bigger veins, and you get one single vein. But portal veins end as well in lots and lots of branches. Portal vein is a short, wide vein that carries blood to the liver from the organs of the digestive system, and it starts from capillaries in the intestines and ends in capillaries in the liver. So it starts and ends with capillaries. Another example of a portal vein is in the hypothalamus in the pituitary, but the one you need to know about is the portal vein, and this is the portal vein. It's this thing right in the middle here, and it's getting blood from the stomach and from the spleen and from the large intestine here, the inferior mesenteric vein, and the superior mesenteric vein from the intestines, and that blood goes into the portal vein, but that then divides up into lots of discontinuous or sinusoidal capillaries in the liver. And so this is a vein which starts in branches and ends in branches, the portal vein. Veins contain 60% of the body's blood volume, and venous pooling can occur when blood accumulates in the lower extremities. If a soldier has been standing on duty for a long time and doesn't move his muscles, he can pull all of his blood in his lower limbs, and he will faint because his brain is not getting enough exercise, not getting enough blood. So soldiers standing on sentry duty are encouraged to move their toes and ankles as they stand, because they don't want to suddenly faint from venous pooling. Physical exercise most important for blood circulation, particularly in a post-operative period when blood clotting is accelerating. Well, that's my presentation. Thank you very, very much. As I say, if you can revise, expand on the text that I've given you this morning, and try and make sense of some of those illustrations as well. See you next time. Thank you.